Okay, good afternoon. Sorry for today, a little bit, delayed because of the previous class. But first, I have to, just talk about homework. Some students pointed out to me, and then I think my, TA also emailed me while I was traveling, and I apologize. I made a mistake in homework problem. So I told the TA to fix and kind of upload. So I just want to talk what I am talking about, and then move on. And then I was wondering why I made a mistake. Yes, of course, I'm not as smart as I think, but because of hurricane, just excuse, I have to split some material, push back to homework 4, and then the previously I made homework attached to homework 3, but I have to move. So I just want to tell. Sorry, everything is recorded. I don't want to show, but what can I do? Homework. I should maybe, okay, homework 4, and then I have to make sure only the problem, not the question answer, right? So this is, right? I may do that, then oops, it may happen. So this problem, question 1, I think I left like drawing figure. I apologize. This is extrusion. So that's why I put like yellow mark, and then now FE is here. Previously was drawing, so then confused students. So I apologize. And then also I think here, question 3, so it was like a question 4, because again this part was part of the question previous homework. So but this one, so I think the here and there I yellow highlighted, but anyway I apologize. I'll be more careful. So hopefully you can complete homework. And then also before I left for my trip to Society of Manufacturing Engineers, I sent the email. So Monday I could not have or hold office hours. So today's office hours, it's going to be extended. So you can come to my office. It's I think extended to 3 or 3:30 or some. I forgot. Do you remember? It's in the canvas. Because I move my, so usually, right? Usually 2:45, right? Yeah, so I think extended to 3:30, yes, because I moved my meeting. So anyway, if you have a question about homework or just in general, please do not hesitate to come to me, even after like usually 2:45, but you can come. I'll be there. Okay? Okay, so let's start today's lecture. So last time I was rushing, and then 5.3.4, and I wrote like section number, and then oops, I noticed 140, right? So I want to start from there. So today, October 16th, and then we will do 5.3.4. So 5.3.4, it's talking about effects of friction. So sorry, I should write effects. Effects. Come on. Okay, so that's I'm going to use the figure 5.37. So I will put this figure 5.37 under this projector 5.37. Okay, so that's page 281. I know it's so. Okay, this one. So this is still part of the forging process, and then this figure wanted to tell the force distribution. So this case, the pink is kind of actually workpiece. So this is A, it's kind of punching, right? Making hole. And then this ram comes down. So then in this case, okay, just this C is not related to A, okay? So then in this case, so the workpiece is not workpiece, punch. And the workpiece, punch has to be, of course, stronger, right? Yield strength-wise, The workpiece, because you are making hole, to workpiece. So then in this case, punch usually, like, I don't know if you can read, like, this is just kind of a recommendation, general. Yield strength, maybe 3 times, more than 3 times, like greater than workpiece yield strength. So that's, maybe that's kind of guideline. But friction related, is more like actually B, and this case. So video I watch, or we watch together at the beginning of forging. So closed die forging, you have die coming down, so like die, workpiece coming down, right? And then, this is pressure distribution. For at the beginning, okay, let's start, right? And then you start, deforming. So not Dr. Shura's class, my class, last time perfectly plastic material, we calculated, right? How much you need force or pressure to initiate, right? Because that was a perfectly plastic material. So regardless how much you push, it doesn't change. The yield strength is consistent, right? Or constant. But if it's strain hardening material, once you deform, then yield strength, or like you see the sigma flow stress, I would say, going to increase, right? So you have to calculate, epsilon, how much you change, depends on height change. Then you will use this epsilon value and then increase, right? So that's how we calculate. But anyway, back to this figure B1 and then B2. You are going to press this top die, in this case, go down, right? So this flush, remember, flush is very important, right? The flush means like, oh, bless you. Flush is this edge. So then once you close, so that's, it's not melting, okay? That's just like, close, like, and cool down. Cool down means compared to the center area, right? And then they could hold, this flush hold the material to kind of flow. Because you want to keep this, create this shape, right? You want to hold all the material inside this cavity die. So this flush, creation is important. And then pressure distribution is going to be, this kind of, like a mountain hill type. But how the generally, the force or even force and pressure, that's of course interrelated. This kind of Y is a stroke in this case, and then force, is Y-axis. So once, you starting from, whatever 0, and then going to, create a flush, because Y is a stroke going down. You create a flush, right? Because then you hold it, and then you really press. So that's why force immediately going to like jump, and then like once okay die this completely close this one, and then go increase, and then complete. So then almost kind of forming, and then complete, and then okay, it's done. So anyway, the point is, from here, initial to flush, it's kind of mild progress. After that, because of the friction, at the especially flush, let's hold, and then sharp kind of, increase. That's, kind of the trend, So anyway, this, and then this, and then the kind of close, and then completion, So this is a cavity, kind of filling. So that's, important trend we want to share. Of course, you can read, I recommend you to read. See, like I put even like a student, right? Marker, same thing I do. I don't know if you do that because you have like maybe, electrical, version of a textbook. But any question? Yes? Please, okay, what's your question? My note? This one? Pressure increase. You can come to me. This is my note. So you can come to my office. I can explain. But in general, any other questions? Just trend, Okay, depends because it's not so simple usually, you know. But trend once you close and then increase and then cavity filled and then complete. That's it. So I think that's about it. And then 5.3.6. Actually, I was going to cover, but this one is like material like a failure. So just only the figure, not like detail. And then I think this section is going to be done. So 5.3.6. So I just want to move on to the figures. Figure 5.41. Sorry. I thought it's next to each other. Oh, sorry, this one. Okay. Okay, I will leave like that. So then this is 5. Okay. 6. So so this is like example of in forging, but similar things happen to bulk forming. So what's happening here? So this is the shear band. Like this is figure 5.41. So if you compress, maybe you could see some shear band. Or even sometimes like a crack. It's not based on only processing conditions. It could be like some sort of material imperfection. It could happen, right? So it's not because of the process, but during this process you may see it. And then like now it's like even center bursting. So center bursting, or even this chevron cavity. So this is like arrow shape. This is how material is going to flow. So deform. So material has to, like especially for this, like D case, D case is like, okay, even extrusion, let's say. So extrusion case from left to right, you are pushing material, right? So depends on this, die angle, like this angle, or even friction. And then also material, preparation. How you are going to, like smoothly press and form. If you are like diameter reduction is too too severe, and then material cannot meet. Cannot meet means of course it's connected, but how they deform, and then they will have this kind of void. But material is processing from left to right. That's why it's kind of arrow shape show up. So once you have this inside, outside you don't see it. It's like a perfect. But inside you have this, and then maybe if you use this, material or parts, like vibration, something, like high vibration, high frequency, atmosphere, maybe eventually it's going to be like a fatigue. Fatigue starts from surface, but if you have some big void, then you will lose strength, and then also you will, kind of change the material, property. I should say plus mechanical property. So that's, and then if you want, you are going to work on this kind of like forming, then maybe you need to understand more like pressure distribution. That's we can actually calculate, estimate, but that's kind of too in depth unless you really need. You don't probably use. But this kind of phenomena you will see even if you are not expert in forging. Even when you make pasta. I don't know if you make pasta by yourself, but or even cookie. Right? Thanksgiving is coming, right? I mean, it's too far away maybe, but you will make some cookies. You will see it. So that's about it. Any questions? Good. I think bulk forming complete. Now we are moving to like sheet metal forming. So that's 5.4. Oh, plate and sheet metal forming, sorry. Yeah. So first, as usual, I want you to understand the process. So I will play video, and then you can get the idea, and then you will see what we are going to study, like, you know, in depth. So let's move on to, I'm not using this one. I'm using this one. So go this way. Okay, not exam. Bye-bye exam, otherwise I will click it, you know, right? And then not this one. Okay. Really? What? If I say what, and then, you know, students like, what, right? Sorry. Really? Oh, here. Sorry, it's outside. I thought I deleted, you know. No. Sorry. Then. Wait. Really? Oh, waste of your time. My time is not so. Come on. I cannot. Okay, I can fix this later, so then I will. My backup plan. Oh. I just want to close it. I'm so sorry. Oh, okay, close it. Okay, let's try. This one. Forming process. Okay, this, you know, first one. You know.
In most shearing operations, the edges of two knives, a fixed lower blade, and a vertically moving upper blade meet progressively from one side of the workpiece to the other to shear the material like ordinary hand shears. The angle at which the upper and lower blades are aligned with each other is called blade rake or shear angle. The distance between the upper and lower blades is known as the blade or knife clearance. Knife clearance is essential for proper shearing and is modified for different material thicknesses and strengths. As the blades come together and contact the workpiece, they partially penetrate the material. This builds up opposing forces in the stock. A crack or tear called the slip plane then develops on both sides of the material, separating the stock. The shear blades typically penetrate the stock no more than 1/3 of the stock thickness before the slip plane occurs. The exact amount of penetration varies with material hardness and knife clearance. On most shears, the upper knife is aligned at an angle to the lower blade of between 1/2 and 2.5 degrees. This angle helps concentrate the shearing force in the exact area of blade engagement between the two knives and starts the fracture on a straight line parallel to the surface of the knives. This inclination also causes the upper knife to move away from the lower knife during the shear. This ensures that the sheared workpiece, called the drop, will not become wedged between the two blades. Bending is a method of producing shapes by deforming the metal beyond its yield point, which is the material's capability to resist permanent deformation, but not past its ultimate tensile strength, which is the metal's ability to resist tearing. The forces applied during bending are in opposite directions, just as in shearing. The bending forces, however, rest between the material's yield point and its tensile strength. In shearing, the forces used are well above the material's tensile strength. As the part is bent, it undergoes a distortion so that the material outside the bend is forced to stretch under tension, and the material inside the bend is forced to compress. Between the tension and compression zones is an area where the material is neither forced to stretch nor to compress. This is called the neutral axis. The neutral axis is important since bending operations are calculated from its location. The extent to which a material deforms, whether in compression or tension, is proportional to the material's perpendicular distance from the neutral axis. The principal terms used to describe bending on press brakes are bend allowance, bend angle, bend radius, and spring back. Bend allowance is the pre-bent length of material that must be included in a blank to allow for any deformation that occurs due to the bending operation. The bend angle is usually the included angle of the bent workpiece. It can also refer to the supplementary angle formed by the two bent tangent lines. The bend radius is a tangent line where the flat, straight section of the part stops and the radius of the bend begins. Spring back is the tendency of the material to return to its original form. Spring back typically ranges from 2 to 4 degrees.
Okay, so we are going to study shearing and bending. There are many others, but I think that's good, enough for fundamental part. Okay, but I think you experience, right, at least one time, like bend, right? You bend the sheet, right, and then sometimes go back, right? That's spring back. That's how we are going to estimate, how we are going to, like die-wise. Okay, if we want to have 90 degree, how much you have to bend because you are going to expect, spring back based on the thickness and also material or mechanical property or material property, right? So that's the goal. And then once we study shearing and this bending, then we will have exam 2. Okay, polymer I included at the beginning. If you look at the list, schedule, but polymer we don't have time for that because of hurricane. So I'm trying to do maybe polymer at the end of the class because after exam 2, I want to go cutting machining side. But hurricane kind of took my time, so going to do that. So then if you start like maybe like worried, so whatever today and till exam 2, so no polymer. Okay, that's gonna be the exam 2 coverage. Okay, so shearing, probably shearing so maybe basically you are going to shear the material, right? Sheet of material, a sheet of metal, you are cutting into small piece. How about punching? So this, cut into small pieces, right? Punching, maybe hole making, right? Make holes, right? Punch, 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 right? Punch, punch. So then that's like you have like cut into like let's say hole making, right? How about blanking? Have you ever heard of blanking?
Like with knife blanks?
So can you explain?
Like they cut out the basic shape of a sheet and then do stuff with it later.
Right. So I don't know if you could. So it's similar to like hole punching, because it doesn't have to be hole punching. You can make other shape too, right? I said hole making, but this can be different shape. Blanking too. So you cut a large let's say some sheet metal, you know. And then blanking wise, you know, to, you know, let's say, large sheet of metal stock around the complete perimeter shape. That's similar to, you know, to produce, okay, just for, you know, just the desired shape. Let's look like that. But I want to explain the difference between punching and blanking. So if you have a sheet, because I wrote hole making, hole can be different geometry, right? So blanking also almost same action, right? Makes sense? So, but this is, you know, punching. Okay, this is blanking. So punching, okay, let's put both hole. You want to make this like that. Same action, you can do that. But punching wise, after, you know, you cut, right? This workpiece comes here, workpiece or some piece coming here, right? It's same, right? So, but the punching wise, this sheet is going to be the workpiece, right? You're punching. So the piece you cut, that's going to be the scrap. You don't need it. But blanking, same thing. But this is going to be the workpiece. This is going to be a scrap. That's a major difference. Make sense? So like, you know, he said, you know, once we cut and then use, you know, for this part, you know, use for something later. So something later means that's going to be the workpiece or part. Good? So then, you know, how to estimate how much force to, you know, to be required to cut, like punching or even, you know, scrapping, punching or blanking. So that's going to be the next. So then equation-wise, you know, very simple, you know, like blanking force or even punching force, you know. Because it's same action, right? So, you know, it's the same. So if we put the force F, and then F equal KOH, you know, then K, that's going to be shear flow strength. Because we are now shearing, cutting, you know. Right? O, that's perimeter. Depends on the how you are going to cut, circular or triangular, whatever, you don't, you know. You don't know. It depends on your application. And then H is a thickness. But this perimeter, how you are going to calculate, that's going to, you know, change depending on the blanking or punching. The reason, you know, okay, this is punch. Punch means blanking also use punch. Okay, punch is a part, tooling. Okay, punching is a action. So this is a punch. You have a sheet, right? This is your workpiece, and then you have a die. Right? And then assume this is like a circular case, okay? Like you are making like a whole case. So I draw this one. Also, video also had some clearance, right? So you have to have a clearance sheet. So if it's diameter case, you know, punch and die, kind of a perimeter, that's 2 times the C difference, right? Because like radial side of C and C, okay? So then why it's different? So let's talk about this. You know, if you cut, okay, then workpiece is going to be like that. I'm exaggerating, okay? Right? It's not like a straight, just like that, right? Because die has a wider, larger kind of, diameter or perimeter, right? So then, once you said, okay, I want to make blank, like hole, like, 50 millimeter. Then you have to think about this, right? So this one is like die side. This is punch side, right? Right? So this perimeter. So this should be the die, diameter. Clear? Make sense? Right? If you want to have, 50 millimeter, blanking case hole, then maybe die has to be a little bit smaller, right? So little bit is 2C, right? C and C. Good? Yeah?
So when punches do, the material would expand as the die?
They don't extend. Yeah, like you shear, right? So this. So because of clearance, it's going to be, if you bend, then it's going to be like that. But ideally, you don't want to, right? Because you want to set the diameter. So then you just want to, kind of press it. The ideally straight. But because of clearance, it's going to be a little bit. Makes sense. We can talk later, Yeah. But it's clear. So the important is diameter. Right? So, let's do some just practice, right? So if I ask question, right? So this is example. Blue. It's okay. Question, right? So blanking, right? So then, you want to have, so now you have sheet metal. 3 millimeter thick, somehow, then this material, this sheet, shear, flow strength, that's, for this case, 200 megapascal, okay? And then this blanking, you want to make a hole, right? And then blanking wise, you want to have this sheet, that's your workpiece, right? No, you have to say no. Don't blindly accept, right? Blanking, okay, go back. I don't want to go, I want to make sure you understand, Okay, I usually don't trick you, but, right, blanking, workpiece. Right? So I said, I want to have a 50 millimeter diameter, I'm just using here, right? Then, die has to be 50, right? Make sense? No. Because if die is smaller, then, okay, if die becomes smaller, it's going to be, go like that. I'm exaggerating, right? So then punch is going to hit the die, right? So die has to be a little bit bigger, right? That's a clearance. Good? So then back to black line. Okay, sorry. Okay, back to the. Oh, I should just use, like, what's okay. Like that, right? Okay, so anyway, this question is not 50. This question, 6 millimeter, you want to make that, hole. Okay, hole means like a part diameter, right? Because we are talking about blanking. So part now it's, sorry. Right, it's just, entertainment, You need that, I need that. So then 3 millimeter, sorry, not 3 millimeter. I said 6, oops, I said 6, this question was, okay, 6 centimeter. That's confusing, but 6 centimeter or 60 millimeter, okay? Okay, so in this case, okay, you are trying to, blanking part diameter, you want to have 6 centimeter, 60 millimeter, but thickness is 3 millimeter, 6 sheet you have. And then how is the force, So how is the force is like equation F equal KOH. So back to F equation, F equal, so K, already 200 megapascal. So this is going to be 200 megapascal, so the mega, right? And then pi d, right? Perimeter, because it's whole. So pi d, d is now 60 millimeters, so 0.06, right? And then we have thickness, right? Right. So then we will have equal 113. If we, this is the Newton, but 113 kilonewton. Okay. So then this is the like force required. Okay. And then now if the penetration depth, so this is entire 3 millimeter, right? And then sometimes we just first of all like one step, this is question wise, if penetration is 45%, that's not even everything, like 45%. And then how the work you spend to penetrate your punch into 45%. So that's like a question, the continuation of the question. So then I'm going to use this penetration. So penetration coefficient. So this is a question, okay? Coefficient. P equal, this is P. Okay, that's 0.45, which means 45%. Then how about the work? Okay. Then W. So we use W equal force, and then how much or how long you press, right? So then now we say 45%. So P 0.45 times H, right? So that's going to be sorry, that's 0.113. Right? Times 0.45 times 0.003. So that's, if you calculate, I believe I'm correct, but if I'm not correct, please, Newton meter. And then if it's, kilojoule, and then, this is joule, right? Kilojoule is 0.15. Or 1.5 maybe. I just stop. Kilojoule. Okay, so that's how we do. Okay. Then little bit complication. Okay, so can I change the sheet? A sheet means like page. It's simple, right? Straightforward. How about if I ask you to make nut or washer? Maybe not nut, washer. So it's another question. Okay, so question 2. Okay, this is a washer. Okay, so then you have now 3.5 millimeter. Starting from big sheet, blank sheet. Okay, so then this washer. You have ID and OD, right? So now we use, So this is OD, but we put like DB. That's 50 millimeter. So this is ID, but we put for some reason DH. Right? So this and then clearance. Right? Because we need to know clearance. And then before, I did not mention. So this is C, clearance. If it's given, calculation-wise, if it's given, that's okay. But usually we can calculate this clearance. Then to calculate clearance, usually we have to have some sort of clearance allowance. That's kind of a coefficient. So now if clearance is, this clearance equal, because we put C, right? And then A times H. So we need to have this value, clearance allowance. Usually empirically you could figure out. Exam-wise I will give, I will give you. So in this question-wise, because otherwise, you cannot calculate, of course. So then clearance is clearance allowance, 0.6. And then this is C equal, clearance allowance. That's going to be 0.06 times 0.0035, right? Because 3.5 millimeter thickness. Okay? Or you can say, this is like a meter version, but you can say, like this is, right? So anyway, yes? No, he has question. H. Thickness. It has to be given. So before we calculate KOH, right? Sorry, that's why I just carry over, so I didn't explain. Sorry, that this is H. But anyway, if you want to, this is meter, right? Because millimeter-wise, you can just keep 0. Sorry, maybe I should draw 3.5 millimeter. Maybe like that, same, So anyway, this case. So how about, then now question-wise, so now variety of color, A, right? Punch and die size for the blanking operation. How about B? Punch and die sizes. Sizes means like a diameter. Okay, for the punching operation. Right? Because first step is you will do actually blanking, right? To make OD. And then second step, you will do punching, right? It's going to be, hole. So then, punch and punching, don't get confused. Blanking punch and punching punch. Okay? Don't get confused. Yeah. Okay, so let's go from, blanking operation. So then clearance, right? So let's just use millimeter just to simplify, So we talk about this, then just millimeter-wise, 0.21 millimeter, right? So then blanking die, because you are trying to make the part diameter is 50 millimeter. So, okay. So that's question, that's like dB equal 50, right? Because you are making part. So die has to be 50 millimeter. And then how about the blanking punch? So that should be, okay, let's put the blanking punch. So then dB punch, okay? So that's, we have dB minus 2C, right? C is a clearance. So then, right? This is the blanking side. So how about the punching side? Punching, then, same thing, we need to have two of them, right? So punching die, so punching die diameter and punching punch diameter. So punching die diameter, DH, 15 millimeter, right? So then punching punch diameter, so D, so then H, P, okay, is DH plus 2C. That's the difference. Ah, sorry, this is a plus. Two one. Sorry, this is spacing for 15.42. Okay, that's how we calculate. So if you understand a little bit like a kind of shape difference, so then plus and minus. So that's a kind of kind of case study.
Why is it plus?
Think about it. Plus and minus, this shape is important, right? Because you want to have a punch diameter, hole diameter 15, right? So if you make bigger, then it's going to be bigger. Do you understand? I don't want to trick you, And then once you figure out, we can talk, okay? Once we figure out, then I ask maybe, okay, how about the force? How much you need, to put the force? Then diameter, right? Like die diameter, always you use. Then times K times H, right? So that's how we do. Any questions? I know we started late, but I think we should stop. So Monday, we will do spring back side, so bending side, and then how we calculate. And then, hopefully I can, introduce some sort of exam, and then you can prepare. And then one more thing, Wednesday, TA, because I have to go to conference to give a keynote. This is my last trip, I promise, I swear. I want to, I miss you guys, seriously, So that's why, but I have to give a keynote. So then I will explain how we are going to manage it. And then I can stand by from Japan, midnight, if you have a question, but it's kind of tough. So I will anyway, tell you how I manage. But please come to class on Monday, and then because it's very important. Okay? Thank you. Bye.